Imagine you build a massive neural network, 50 layers deep, millions of parameters, all the cloud compute you could ever want. But you make one tiny mistake. You set every activation function to be linear. Suddenly, something weird happens. Those 50 layers mathematically collapse into a single, basic linear transformation. You just spent thousands of dollars in compute to build a very expensive, very slow straight line. As developers, we are taught how to build neural networks. We import libraries, we stack layers, we hit train. But if you don't know why those pieces exist, you're just guessing. You're treating the network like a black box. Today, we are breaking open that box. We are going to answer the 8 fundamental questions most developers secretly can't answer. By the end of this video, neural networks will stop looking like dark magic and start looking like a brilliant, coherent system of software engineering. Let's get into it. So, question number 1. Why must activation functions be nonlinear? We just saw what happens when they aren't. If one layer multiplies your input by a matrix and the next layer does the same, you haven't added complexity. Mathematically, if vector x is multiplied by matrix W1, then the result is multiplied by matrix W2 is exactly the same as x multiplied by m, where m is the W2 times W1. It's just one matrix multiplication. A linear model can stretch space, rotate it, or shear it, but it cannot bend it. Look at these two groups of data. No straight line can separate them. A nonlinear activation changes the game. It lets each layer fold and warp the data before handing it to the next layer. The true power of a neural network isn't the matrices. It's the constant alternating between linear transformations and nonlinear bending. But if bending space is the secret, why do we go deep? That's question 2. Theoretically, a shallow network that is wide enough can approximate almost any function. This is called the universal approximation theorem. So why do we stack layers? Because of efficiency and composition. Think about how you write software. You could write one gigantic function with 10,000 lines of code to run your entire app. But you don't. You write small, modular functions that build on each other. Neural networks do the same thing. Pixels form edges. Edges form shapes. Shapes form objects. Depth gives the network a way to reuse increasingly complex features. Depth isn't magic. It's just computational composition. Now that we know we need nonlinearities, question 3. Why do we always use ReLU? Negative values become 0. Positive values pass through exactly as they are. For something sitting at the heart of advanced AI, it looks completely brain dead. But let's compare it to the old school choice, the sigmoid function. Sigmoid looks elegant. But for really high or really low inputs, the curve flattens out. A flat curve means a derivative of almost 0. When we try to train the network, those tiny derivatives multiply together, and the learning signal completely dies. ReLU is brilliant because on the positive side, the derivative is exactly 1. The signal passes through perfectly. Activation functions aren't chosen because they look mathematically pretty. They're chosen as engineering trade-offs to make training possible. Which brings us to how the network actually learns. Question 4. What is backpropagation actually doing? People often describe backprop as the intelligence of the network. It's not. Think of a network as a long chain of functions. We get a prediction at the end, we measure how wrong it is, and we want to know, if I tweak this specific weight in layer 2, how does it affect the error at the very end? The math for this is just the chain rule from calculus. But calculating it from scratch for a billion parameters would take forever. Backpropagation is just a highly efficient bookkeeping trick. It moves backward through the graph, reusing intermediate calculations so we don't repeat work. If you're a developer who has used dynamic programming or memoization, that is exactly what backprop is doing. So backprop gives us the gradients. But what is a gradient? It's not a GPS map pointing to the perfect solution. It is just a local slope sensor. The gradient simply tells the network, if you change this weight by a tiny fraction, the error will go up. So the optimizer takes a tiny step in the opposite direction. Because it's only a local sensor, training is just a massive loop. Guess, check the slope, take a step. Guess, check the slope, take a step. But wait, how do we get a usable guess in the first place? That's question 6. Why Softmax? Often, the final layer spits out raw, unconstrained numbers called logits. They might be negative. They might be huge. If you're building a classifier, you want clear probabilities that add up to 100%. Softmax uses exponents to force every number to be positive, and then divides them by the total to give you a valid probability distribution. The equation looks like this. It's a translator. It translates raw machine math into a language the loss function can easily evaluate. So we have a deep network, we have gradients, and we have probabilities. Why did it take us decades to make deep networks actually work? Question 7. Where do vanishing and exploding gradients come from? Remember backprop? It multiplies derivatives together backward through the layers. If those derivatives are smaller than 1, say 0.5, multiplying them across 50 layers makes the gradient functionally 0. The early layers never get the signal to update. That's a vanishing gradient. If the numbers are slightly larger than 1, they multiply into infinity and your network crashes. That's an exploding gradient. Building a deep network is easy. Building one where the learning signal survives the trip from the end to the beginning is the hardest engineering problem in AI. Which brings us to our final question. How we fix it? We used a few brilliant tricks. First, smart initialization. We mathematically scale the starting weights so the signals don't immediately blow up or vanish. But the true hero is the residual connection. Instead of forcing a signal to grind through every single layer, we build an identity shortcut. The layer learns the difference, the residual, while the original signal bypasses it. During backprop, gradients now have an easy, high-speed highway to travel all the way back to the start of the network. This one trick is why we can now train networks with hundreds of layers. Now that you see the gears turning, let's look at the 3 most common pitfalls developers make. Number 1, treating it like a black box. If you don't know the math, you can't debug the system. Number 2, assuming deeper is always better. As you now know, depth adds massive optimization hurdles. Don't add layers unless you need hierarchical composition. And number 3, copy-pasting code. Don't just slap a Softmax layer on your network if you're doing regression. Use the right tool for the mathematical problem you're solving. A neural network isn't a magic wand. It's a carefully balanced software architecture. Remove nonlinearities and the depth collapses. Add depth and optimization breaks. Fix the signal paths with skip connections, and deep learning becomes a reality. Now, earlier we talked about how neural networks bend space to solve problems. But what exactly is that space? To truly master AI, you have to understand how machines perceive words, images, and logic as physical locations in a high-dimensional universe. It's called a vector space, and it powers everything from ChatGPT to search engines. I've put together a full breakdown of exactly how vector spaces work and how you can use them in your own code right now. Click the video on your screen, and I'll see you over there.